The Neogene is the second of the three periods of the Cenozoic era, and it represents a continuation of the transformation of Earth's landscapes into their modern forms. In western North America, this includes the Basin and Range province, like here at Death Valley. This is Devil's Golf Course, which is at the bottom of the Death Valley Basin. This salt playa here is over 270 feet below sea level. In fact, it's the lowest point in North America. Looking off to the west there, that's the Panamint Range, and Telescope Peak up in the snow is over 11,000 feet above sea level. So over 2 miles of vertical difference. This tectonic basin got its origins in the Neogene and continues to develop today. Landforms changed during the Neogenes, as did the lifeforms. We'll see different mammals flourish and develop through this time period, but also birds, like the terror birds. This is Forus raucus. It's a descendant of the dromaeosaur dinosaurs of the Cretaceous. Just as fearsome as those dinosaurs, these terror birds were one of the main predators on land. Here having a serious discussion with a primitive bear. One last thing that characterizes the Neogene is the rise of grass. So in this picture here we can see grass pretty much covering the ground in all directions. The Neogene period itself spans the range of 23 million down to 2.58 million. So looking at it on the time scale here, it is the middle of the three Cenozoic periods, the Paleogene, the first one, then the Neogene, then the Quaternary. So starting at 23 million, going down to 2.58 million. It has two epochs, the Miocene and the Pliocene. The Miocene, the earlier one, 23 down to about 5.3, and then the Pliocene is just a short few million years, the end of the period. This is also known as the late tertiary. In fact, the tertiary again is the older term which refers to both the Paleogene and Neogene. Now we use Paleogene and Neogene. Early tertiary, late tertiary. Sometimes people talk in terms of a middle tertiary, and that would be more or less the early Miocene and late Oligocene here. The geography of the Neogene is very similar to that of today. We see continued ocean basin rifting, the North Atlantic and South Atlantic, continued mountain building of the Alps and the Himalaya and the Andes. When you look at this picture of the world during the Miocene, about 14 million, it looks almost like today. So it's like, what's different? Well, one difference is here you can see North and South America are not connected. So there still is free flow of water between the North Atlantic and Pacific Ocean basins. And also over here in the Mediterranean, the alpine orogeny is still ongoing, and there's still areas covered by shallow marine water. But everything else looks pretty similar, including ice at the poles. And the ice cap that had started to develop at the end of the Paleogene in the Oligocene epoch continues on into the Neogene. So this ice cap will enlarge over this period and keep doing so until today. Let's look at Ron Blakey's paleogeographic globes for the Neogene. These are for the early Miocene about 20 million years ago. So you can see a very striking similarity with the modern day Earth. Okay, we're even seeing ice starting to accumulate in the northern hemisphere here, most likely. Parts of Europe are inundated with shallow marine environments, as is Florida. So there's some minor differences. You can still have open passageways between Pacific and North Atlantic here. Those are minor changes. Everything else is pretty similar to that of today. The Red Sea and Gulf of Aden haven't opened up yet, as the hotspot here in East Africa has only just started to rift the Arabian plate from the African plate. And the Alps are still progressively growing. Looking more closely at North America, you can see what it looked like about 15 million years ago. And again, the striking difference here would be the absence of Florida. It's still a shallow marine environment, many reefs and carbonate platforms, much like in the Caribbean and Bahamas today. Okay, we have connection of Eurasia with North America here. Call that Beringia. That's the land bridge connecting both. But everything else is very similar. Let's move forward a few million years to the late Miocene. Pretty similar story. And then finally to the end of the Neogene and the Pliocene. Very similar to that of today, where we can see Alaska, tail of Alaska, we can see the Baja Peninsula. So one reason we're not seeing a whole lot of change here is we've only covered about 10 million years of geologic time. Many of these other windows of geography that we've been looking at cover much longer lengths of time, so we see more changes. Let's back it up. One thing to look at is the evolution of the transform boundary on the west side of North America here. So this is about 15 million, middle Miocene, and the San Andreas transform is in existence here, and part of it is moving this way and North America is moving this way, so a right lateral transform. So this is middle Miocene, late Miocene, Pliocene. So through the Neogene we're seeing the northwestward translation of the Baja Peninsula as the Gulf of California opens up and there's movement along the San Andreas. In western North America, the geography is changing quite a bit. And looking at a time sequence here shows the development of the landscape province known as the Basin and Range. It occupies this area from eastern California across Nevada into Utah, down into Arizona, even down into Mexico. That's the Basin and Range physiographic province. So it was created pretty much when the San Andreas transform was created and the end of subduction. There was an end to compressional tectonics. If you have a vise and that vise is constantly squeezing and then all of a sudden you stop, there's a relaxation. And this relaxation caused extensional tectonism, at least in the beginning. And the result of that are downdropped basins along normal faults caused by the pull-apart tensional stresses. And those are separated from each other by intervening mountain ranges, so the Basin and Range. The Sierra Nevada on the west side represents the western margin of the Basin Range province, and on the eastern side it's the Colorado Plateau. So as the Basin and Range starts to develop, these other landscape features do as well. So the Sierra Nevada mountain range in California starts to become a landform province during the Neogene, as does the Colorado Plateau, which is more or less centered on the Four Corners region. Here's looking to the west at the Sierras. That is the western margin of the Basin and Range. Here we can see the area that we're talking about, Basin and Range, as it develops over time during the Miocene. It's a period of crustal spreading. There are also, along western North America, more terrains being added because the whole boundary is not transformed, just this part of it. Farther south it's still subduction zone, and farther north it is as well. And so we're still getting terrains being added onto the western margin. Neogene tectonics, continuation of the mountain building processes in the Himalayas, the Alps, continent-continent collisions going on there. The ocean-continent convergent boundaries of the Andes and the Cascades are also continuing. So whether it's continent-continent collisions in Europe, in Eurasia, the Alps, in the Himalaya, or ocean-continent convergence with the Nazca Plate here and the South American Plate forming the Andes, or even the Farallon Plate in North America forming the Cascades. It's a continuation of what we've been seeing. In fact, farther northwest, we'd see more accreting terrains along that boundary up into Alaska. Also, in the Central America area here, we're starting to see continental fragments come together, and in the area between North and South America. These would eventually join by about 3 megaannum, is when we think North and South America connected. They've been apart for a long time, and now for the first time they've been joined, although it's very narrow, the Isthmus of Panama. So only a few tens of miles wide in various places, and it's a fairly complex plate tectonic environment. But finally there's a connection between the two major supercratons, the North American and South American. And we've now shut off that free flow of water between Pacific and Atlantic. That's going to have major consequences, as we're going to talk about. And there's several major hotspots that are continuing to form, and that includes Hawaii, Iceland, and even Yellowstone is going to originate in the Neogene and continue on to this day. Well, in Western North America, things continue to develop. So looking at the northwest part, here we have North America, and here's the subduction zone. Still, this is the Farallon Plate being subducted underneath North America, and it continues to this day. We don't call it Farallon anymore. The modern names of the Gorda Plate and Juan de Fuca Plate and the Explorer Plate are what were formerly known as Farallon. Here's the mid-ocean ridge that creates the Farallon Plate, and then of course on the west side of that is Pacific Plate. Here it's being subducted underneath North America, and you're getting the continental arc developed on top. This shows a cross-section of this region. Here's the Juan de Fuca Plate, or Farallon, and you can see that the arc itself, which is the Cascade Mountains, is being built on top of a fairly complex assemblage of terrains that have been added on over the past few 100 million years. Remember the Franciscan terrain, which was an accretionary wedge terrain back in the Mesozoic? That forms some of the basement for the Cascade Mountains. If we look at the picture overall on the west coast here, during the early Miocene, about 20 million years ago, here is the Farallon Plate, now Cocos and Juan de Fuca. Here's Pacific Plate. Here's the mid-ocean ridge. Remember, at about 28 million or so, the Farallon mid-ocean ridge began to be subducted underneath North America. And so over the last 8 million years, it's progressed to this point. And with continued subduction of this mid-ocean ridge, the San Andreas transform in between gets longer and longer. So this is how much it's grown in about 8 million years, from the Mendocino area here just north of San Francisco down to Los Angeles. And then into the late Miocene, you can see it's more than doubled, almost tripled in length, because continued subduction of the mid-ocean ridge has lengthened that transform fault significantly. The other thing that's happening here, remember, is underneath North America, if you extended the mid-ocean ridge here, there would be Farallon Plate here, but to the left of it there wouldn't be. Because once it starts subducting, there's no more mid-ocean ridge process going on, no more plate, oceanic plate being made. So the slab window starts to form. And so here it's fairly small, but here it's much bigger. And today, in modern day times, it's even larger. So this is what we have today in North America, all the way down into Mexico. And we can see Baja is on the Pacific Plate, and it's being translated north along the transform. Let's talk a little bit more about the southwestern margin of North America here. It's still the continued subduction of the Farallon mid-ocean ridge underneath North America, and as that happens, the San Andreas transform boundary grows in length. If you remember, back in the early Oligocene, the Farallon Plate was being subducted underneath the entire margin of North America. And at about 28 million during the Oligocene, that was when the first part of the mid-ocean ridge started to get subducted underneath North America. So with time, more and more of it would be subducted, and as that happens, the San Andreas transform boundary would start to grow in length. If you look at this map here, this is early Oligocene, this is early Miocene, maybe about 20 million. The mid-ocean ridge, if you extend that this direction, it would end about here. This area right here is that slab window that I referred to. Okay, so that's the area underneath North America where there's no downgoing slab. Okay, this is the remnants of Farallon here and here. There's Farallon plate underneath this region, but right here there's no more plate because the Pacific plate now is moving kind of in the same direction as North America, and there's no more plate being made, so that's the slab window. So with time, that's going to get bigger and bigger. If you remember, when this first started in the late Oligocene at about 28 million, the Farallon mid-ocean ridge starts to get subducted, and the left side of the mid-ocean ridge, which is the Pacific plate, is moving off to the west, the same direction North America is moving. Okay, so it more or less isn't getting subducted. It's moving slightly different direction. You have a transform boundary. The minus means this side's moving away. The plus means it's moving toward. But the other side of the Farallon mid-ocean ridge is the Farallon plate. It keeps going. It keeps subducting down, and so that gap right here, where there used to be mid-ocean ridge, it keeps widening, widening, widening. This is the slab window. Because the mid-ocean ridge is now subducted, mid-ocean ridge processes pretty much cease. We're not making oceanic plate anymore. No more plate. The plate keeps going. The window gets bigger. The effect of this is it allows the hot asthenosphere, or at least the heat from the asthenosphere, to well up through this gap and contact the North American plate here. And so for a very long time, from the Paleozoic through the Mesozoic until now, there's been a subducting plate going down underneath North America with asthenosphere underneath. Now for the first time, there's a asthenosphere being able to come up right underneath North America. That's going to be a change. So right now, when we look at the extent of the slab window underneath North America, here's where the mid-ocean ridge is now, just south of Baja, and it more or less has a bunch of little segments going up the Gulf of California. But the slab window has progressed to a size like this. So underneath North America, there is no downgoing slab in this whole region. The remnant of the Farallon plate is down under here and over here, but this is the region that is underlain by no slab. So sometimes it's called a slab gap or slab window. Well, post-subduction tectonics have been dominated by the formation of the San Andreas transform. So shear stresses forming transform faults and strike slip faults, but also the upwelling of the asthenosphere and the heat and the crustal spreading, tensional stresses forming normal faults, various kinds forming the basin and range landscape itself. So the basin and range disturbance, it's not quite an orogeny, but it's a rifting event. And it's where Western North America is trying to rift apart very slowly. And it's kind of a wide rift. It's not a narrow, focused kind of thing. It's a wide area that's spreading behind the plate boundary. So this really gets its start in the early Miocene, and it continues to this day in certain parts of the basin and range. The recipe for this is thick crust, laramide orogeny, thicken the crust. We have high heat flow because the continental magmatic arc swept back to the west. That heat added to this thick crustal sequence, and now there's no plate convergence, so everything is allowed to relax, a fairly unstable situation, so everything is extending now. Crustal extension is the result, and this is what's forming the basin and range. As it extends, it's thinning the crust this way, so it's thinning the crust as it extends. And so this is how a continental rift starts to form. In this case, it's a fairly wide rift. And the area of the basin range goes from California to Utah. This is what's called the Great Basin, which is much of present-day Nevada, all the way up into southern Idaho and Oregon. And then there's the southern basin range, which includes the Sonoran Desert and much of the Mojave Desert, Mexican highlands down here. So this landscape here is called the Basin Range. So it's the area where North America is under tensional stresses and trying to rift apart to some degree. Early on, the rate of extension is fairly high. And so we see a lot of low angle normal faults being formed. So very low angle, maybe 20 degrees, less than 30 degrees. Hanging wall sliding down. So those are low angle normal faults. And we call those detachment faults. So as the upper plate slides down, the lower plate's coming up, exposing deeper levels of the crust and forming what we call metamorphic core complexes. So these low angle normal faults are major features. Typically there's one major one and then there's a bunch of other secondary ones above it where the hanging wall is being split into smaller fault blocks which are all rotating. Many of these faults are curved, so there's a lot of tilting of the layers within the blocks. So again, if you see layers that are tilted like that, that commonly means there's a fault that's curved that's causing the tilting. It's not just down dropped, it's actually moving along a curved fault plane. So this is the basin and range disturbance, and it gets its start in the early Miocene, and it's relatively rapid, and we get a lot of fault block mountains, and at first they're very large and high compared to the basins, which are fairly limited, and over time the erosion of these mountains will cause them to get smaller, and the basins will receive that sediment. Basins will get deeper and wider. Well, if you remember what Arizona was like in the Paleogene, we had highlands in the south and they were draining off to the north. We had the rim gravels. Well, this basin and range disturbance would change that. With the crustal spreading, we'd have thinning of the crust, mostly in southern Arizona and points farther west, which would lower the crust eventually so that they would be at a lower elevation than in northern Arizona. So the effect of this, here's a geologic map. We're going to look at stream flow in the Paleogene, specifically the Eocene and Oligocene. The stream flow was off to the north, and it was depositing these rim gravels up on the Mogollon Rim. That was the picture before, but then, because we had highlands down here, lower areas up here, during the basin range disturbance, this area would get lowered, and the basin range would start to form. The Colorado Plateau, which is not being extended, would remain at or above where it used to be. So the Colorado Plateau would be raised and the basin range would be lowered. So we're getting kind of a flip of the topography. And the streams then would respond by reversing. So during the early Miocene, as the basin and range spreading initiated and progressed, we would see evolution of the basin and range in the south and the Colorado Plateau in the north, and eventually a reversal of the drainages. So we can map all this out by looking at stream deposits of this time, and we can see the earlier deposits point to flow off to the north. Sometime during the early Miocene, we start to see south-flowing streams across central Arizona. This is called the early Miocene drainage reversal, and it just reflects the change in elevations of the two different areas. Really, it reflects the formation of the basin range in the Colorado Plateau. So this is what we have today, where the plateau is higher and streams drain off to the south. The stream deposits are telling us there's a change in the landscape and the formation of the basin range and the Colorado Plateau physiographic provinces. That was in the early Miocene. And it continues in many places in the basin range today. In Arizona, this ended in the Miocene. So a little bit later in the basin range disturbance, during the middle and late Miocene, extension rates would slow down. And so with the lower rates of extension, the faults would respond by becoming more high angle. So high angle normal faults were formed instead of these low angle detachment faults. And the effect of that is to create deeper fault basins. So this block diagram shows high angle normal faults on either side of this basin. It's a fault bound basin. Faults on either side, that's what we call a graben. And the mountain ranges in between. So commonly Horst and Graben topography. The Horst being the mountain range and the Graben being the downdrop block. These probably weren't uplifted too much. They stayed the same. It's just these intervening areas were dropped as everything spread out. These are the Pinaleño Mountains. This is a basin range mountain range in southeastern Arizona. Here's a depth to bedrock map of the Phoenix area. The colorless areas are the mountain ranges. Here's South Mountain, Sierra Estrella, Superstition Mountains, White Tank Mountains. And these colored areas are depths to bedrock. And the orangish colors are more shallow depths to bedrock, maybe a few hundred feet or so. Whereas the blues and greens, the other colors, represent deeper and deeper and deeper to hit bedrock. So what it's showing is where there are subsurface basins. There's one here in the East Valley of Phoenix. This is called the Higley Basin. Here's the Paradise Valley Basin. MCC is right about here. Here's the Luke Basin, and there are other ones around. So these are all deep basins. Many of them are 8, 9, 10,000 feet deep. And those were created during this latter part of the basin range disturbance where you had these faults dropping the basins down, and then they'd fill up with sediment over time. In the late Miocene, this extension starts to drop off in the south, but in the north it progresses. So at about 8 million is when we see extension like this end in Arizona. So no more active tectonics, and so the mountains have been eroding for the last 8 million years. So the mountains have been getting smaller and the basins have been getting wider. That's in the southern areas of Arizona. But as you go north, you notice that mountains in Nevada are still pretty big. Yeah, there's some big basins, but the mountains are still big and high. It's because the tectonics is still going on there. So as long as there's tectonics going on, you could still have this relief being formed. It's still kind of keeping up with erosion. Once the tectonics shuts down, then erosion takes over, lowers all the mountains, makes the basins bigger. The northern part of the basin range is still forming. This map here shows some other elements that are forming during the Neogene. Sierra Nevada mountains are over here. That's the west side of the basin range. Here's the Cascade Arc, Columbia River flood basalt area, Yellowstone hotspot. So the basin range is this wide rift between the Sierras and the Colorado Plateau over here, and the Wasatch Mountains in Utah. Well, we can talk about the Sierra Nevada mountains now. They get their start in the late Miocene, and they continue forming till this day. They have their origin with the formation of the Basin Range province. They represent the west margin of the Basin Range, which, as we talked about, is a continental rift. Here is the Sierra Nevada mountains themselves in central California, and this is a cross section showing that the Sierra Nevadas themselves are a huge crustal block, and off to the east the crust has been extended into individual mountain ranges and basins. So this is the Basin Range here, and this is the westernmost fault of the Basin Range, and then here's the Sierra Nevada. And the Sierra Nevada themselves kind of a huge tilt block which has been tilted off to the west and forms this slope here, and then the Great Valley and Coast Ranges are off to the west in the San Andreas. So the Sierra Nevada themselves are this huge competent block of granitic and dioritic plutonic rocks. Remember, this used to be magma chambers that were feeding a continental arc during the Mesozoic. That's what these rocks are. Here's the view from the Lone Pine area of the east side of the Sierras. This is the Western Basin Range. All the sagebrush desert here, dry because it's a rain shadow desert. These are big mountains and they're blocking the flow of air from the west. So the moisture gets dropped out on the west side, but the air keeps moving. So you get these winds that are coming down off the Sierras that are dry, and you get a rain shadow desert. which is much of the Great Basin area. So we see a lot of seismic activity around the Sierras too, because the San Andreas is coming up through like this, and the San Andreas has to bend here because it wants to keep going straight, but it hits the Sierra Nevada, so it bends off to the west. And there's a lane on the east side of the Sierras that's still getting major earthquake activity. It's called the Walker Lane, and large magnitude earthquakes occur frequently along the east side of the Sierras, and that's just a reflection that it's still trying to spread on the east side there as well. But this is a big normal fault on the east side of the Sierras, like near Lone Pine and Owens Valley. Well, finally, in the Neogene, right at the end of the Miocene, we see the Grand Canyon. So in late Miocene is when we think the actual hole in the ground, at least most of it, formed. The canyon was probably there to some extent before, but the through-going drainage of the Colorado River, we think, was established less than 6 million years ago. Now, this is a controversial topic, and it's been fought over for years, but we're finally coming to some consensus with additional data and interpretations that the 6 million year number is the correct one, at least for the formation of most of the modern day Grand Canyon. We think that before the Colorado River was a fairly old age stream, if you will, meandering, spending most of its energy meandering horizontally back and forth, big meander loops. And then this uplift event happened, and the stream started cutting down towards the base level. The reason why it's doing this horizontal movement here is it's very close to its base level, which is what a stream wants to get to. The farther it is from its base level, the more it's going to want to cut down. Well, this uplift event happened, and the streams started cutting down right where they were flowing. And so we start to see not only slot canyons, but incised meanders. So old age stream patterns, but with very youthful stream canyon profiles. This is indicative of an old age stream landscape that has been rejuvenated and uplifted so that the streams are cutting straight down. We think uplift happened about 6 million years ago, forming much of the modern day Grand Canyon. And why this uplift happened 6 million years ago was likely the overall effect of this thermal pulse coming from the asthenosphere through the slab window. As the slab window got wider, the effects of that heat coming up through the slab window on the bottom of the North American plate were such that there was uplift, and this is the result. This is basically Chapter 7 in Dr. Bob's dissertation. This is one of my conclusions. Never published the novel, though. So 6 million years ago is when the Colorado River flowed through the canyon. Now, the history of the Grand Canyon is colorful and there's a lot to it, but that's the bottom line about how the actual canyon was formed. The canyon itself is young, but the rocks in the canyon are old. So the rocks are old, the canyon is young. Let's look at some rocks. Neogene rocks. In the Pacific, the Hawaiian Islands are late Oligocene to recent in age, so there's Neogene rocks in there. And if we look at the whole Hawaiian Island Emperor Seamount chain, they all have their origin with the decompression melting of the mantle right here with the Hawaiian mantle plume. Even way back in the day, 60 million years ago, this was going on, forming a volcanic mountain eventually, which would get above sea level and form a volcanic island. That would have been the hotspot. And then that Suiko volcanic island would slowly get taken off the hotspot, and you get another one, and then another one, and then another one. And so this whole line of seamounts here used to be volcanic islands, and the farther they get taken off away from the hotspot, the cooler they get, they start to subside, and sooner or later they're down below the waves and they get eroded and they form seamounts. This whole trace here of the Emperor Seamounts and eventually Hawaiian Islands is a record of the movement of the Pacific Plate over this Hawaiian mantle plume. So all these used to be volcanic islands, or at least a lot of them, some of the major ones. We know because some of them are flat-topped, and that means that they were shallow enough to be eroded by waves. These flat-top seamounts are known as geos. from 60 million all the way down to 43, the Emperor Seamount chain, and then the Hawaiian chain here. Much of it is still submerged. Midway is an island. That's Oligocene in age, but this stretch right here is all Neogene, early and late Miocene. Now we're getting into the Hawaiian Islands themselves. A few of these islands are Neogene, and then from more or less Molokai, Maui, and Hawaii, these are all Quaternary and up till now. So there are a few Pliocene-aged Hawaiian islands, of which Kauai and Oahu are prominent ones. The Pali Coast on the north shore of Kauai, just outstanding. This is mostly mafic volcanics coming from eruption above that mantle plume, in this case with Kauai about 5 million years ago. So if you like mafic volcanics, Hawaii is the place to go. You can see ancient ones and also active ones. Let's move over to western North America and talk about the Columbia River flood basalts. These are Miocene in age and started forming about 17 million years ago. They erupted about 175,000 cubic kilometers of mostly basaltic lava. We've been talking about flood basalts typically in the range of millions of cubic kilometers, so this is just a little one. But all flood basalts really get their start when a mantle plume first forms and starts to interact either with an oceanic plate or a continental plate. In this case, it's the North American plate. So there's what's called the Yellowstone mantle plume that's coming up underneath North America about 17 million years ago, causing it to uplift and to fracture a little bit, and you're getting decompression, melting of the mantle plume and eruption of these mafic lavas. So a serious volume of these mafic lavas. This shows the geologic map of Washington and Oregon, the Cascade Range and its volcanoes. In green here is the extent of the Columbia River flood basalts. So the Cascades volcanoes are built on top of the Columbia River. Here's the Columbia River right here cutting its way off to the west towards the Pacific. And that's what the group gets its name. So there's a number of different eruptive groups here. This is what they look like. Flow after flow after flow. Mafic lavas along the Columbia River. Fairly stark landscape. Again, it's behind the Cascades, so it's a rain shadow desert. That's why it looks so dry in many cases. This represents the initial activity of the Yellowstone mantle plume, the mantle plume that eventually formed Yellowstone where it is now. Columbia River flood basalts. There is no real extinction event related to this eruption. Well, let's stick with the Yellowstone mantle plume for a second. So it started at about 17 million, formed the Columbia River flood basalts. Then a little bit later, the late Miocene and into the Pliocene, as the North American plate would move over it, it would start forming what's called the Snake River Plain. This is where you're still getting decompression melting, forming the basaltic layers, but now a lot of those magmas are interacting with the North American plate in the continental crust there, and you're starting to get felsic magmas formed. In terms of the volcanism, it's what we call bimodal. There's two modes. One is this interaction with the crustal melting, felsic, and the other one's mafic. The sequence of lots of felsic magmas and then mafic magmas as well. This caldera-style felsic volcanism is, again, what we call ignimbrite volcanism. So a lot of explosive pyroclastic activity, volcanic ash flow sheets and tuffs. Where the mantle plume started in the Columbia River area, as the North American plate progressed, we see a line of eruptive centers, and this is the Snake River Plain, and it points towards where the mantle plume sits today, right here at Yellowstone. It's an age progression of different volcanic areas from the Miocene to the Pliocene. And here's a bigger picture showing the Columbia River area and then the Snake River Plain. So it's really a hotspot trace, much like the Hawaiian Islands, except the Hawaiian Islands and Emperor Seamounts is on an oceanic plate. This hotspot trace is on a continental plate. The only difference here is it's a continental plate. And so we're getting the mafic volcanism from the mantle plume part, but also the interaction with the continental plate is giving you felsic caldera-style ignimbrite volcanism as well. Okay, so a progression, a slow march to younger and younger eruptive centers till we finally get to where we are today at Yellowstone. Let's talk about felsic volcanism a little bit more. In the early Miocene, this was going on across western North America in various places. Not just the Snake River Plain, but farther south, we're seeing the end of subduction-related volcanism down in Arizona. So the last subduction-related caldera-style eruptions are early Miocene in age in Arizona. These are caldera eruptions. Again, we call that ignimbrite, vast amounts of volcanic ash blown into the atmosphere, come back down in terms of ash flows and ash fall. So huge thicknesses of ash. We think that this emanates from lots of crustal melting. Commonly, there is a larger volcanic complex above it, maybe a stratovolcano or two, but it is venting at more than one spot. So typically there's multiple fissures here that are erupting felsic ash, very powerful pyroclastic eruptions. And we're drawing down the magma chamber rapidly from these multiple vents. And so the roof overlying the magma chamber becomes unstable and eventually collapses, forming a hole, which we call a caldera. So that is the simplistic version of how a caldera forms. And this can repeat as magma then reinflates. This chamber pushes this up like a piston, and the whole thing starts all over again. So you can get what are called resurgent calderas. This would represent kind of the last of the subduction-related volcanism, at least in Arizona. The Superstition Mountains off to the east of Phoenix represent this kind of volcanism. This occurred over a span of a few million years, from about 21 to 18 million. We used to think it was more from 25 to 15 or so, and then the Arizona Geological Survey went in, and I was part of that mapping project, and we mapped a whole bunch of the range and dated it with argon methods and correlated things, and we actually figured out, instead of 3 big calderas that erupted over 10 million years, it was actually more like 1 big caldera which erupted over a few million years. That's the Superstition Mountains. Here's Saguaro Lake, and one of the cliffs here is formed from felsic volcanics. There's lavas and mostly ash. Some of it is welded, so you get things like welded tuff that are extremely resistant. All these yellow areas down here are either Eocene or Oligocene or Miocene in age felsic volcanics. So superstitions are here. There are other places in southwestern Arizona, like the Kofas, are early Miocene in age as well. Chiricahuas are more Oligocene in age, so they're older. Because remember, the arc was coming this way. So these spots right here were the last of the arc-related, subduction-related volcanics. Well, if subduction was ending and all that ignimbrite volcanism was ending, what was it replaced by? Well, in many places, like the Snake River Plain, you still had mafic volcanics being erupted. In Arizona, we'd see a switch to more mafic volcanism as well. After the early Miocene and the end of that caldera-style volcanism, we'd see more mafic volcanics erupted, so more basalt-dominated, and many of these are in orange here. So these are basaltic volcanics, and some of the red areas are even Pliocene in age. Some of the earliest Springerville volcanics in the San Francisco field and the Uinkarets, some of the earliest ones there are Pliocene in age. All these orange ones are certainly Neogene in age. The Hopi Buttes, the volcanics stretching up the I-17 corridor, in the Lake Mary area, etc. So these are all dominantly mafic volcanics. One representative formation is the Hickey Formation in central Arizona. Flow after flow after flow. This cliff right here is in the Agua Fria National Monument, so it's right in this area. north of Phoenix. And these cliffs here are very resistant lava flows, and there's 1, 2, 3, at least 4 individual flows making up that cliff. And they are overlying a bunch of sediments here, interbedded with even older lavas. So this is the Hickey Formation right here, which represents this mafic volcanic activity. Here they have an age of about 11 million up top there. If we're making these basins and filling them up with sediment, then we have basin fill. So it's a pretty glorious name for all the clastic sediments that are deposited in these basin and range basins. Whether it's a graben, faults on either side, or a half graben, much like Death Valley, these low areas are receiving sediments from the surrounding mountains, and they're filling up with sedimentary breccia and conglomerate near the mountain fronts, and farther away from the mountains the sediment size decreases and you get more sands, finally muds, and even evaporite in the basin centers farthest from the mountains. It's all called basin fill. Here's Death Valley. This is up on top of one of the alluvial fans right near the mountain front. Huge coarse-grained blocks that haven't traveled very far from the mountains. And streams will eventually move these blocks farther down and they'll erode, become more rounded with distance. This is out in the middle of Death Valley itself, so more of the playa. Finer grained sediment. Here it's a sea of evaporite, Devil's Golf Course. Not all basins have the evaporite deposits like this. Some of them never receive the water that evaporated to form these deposits. Other ones are typically just filled up with fine grained sediment. Here it looks kind of pinkish. So that's just muddy sediment deposited in quiet water. Here's more coarse clastics, basin fill gravels. San Pedro Basin is off east of Tucson. So basin fill are these neogene clastic sediments filling up these basin and range basins. The climate during the Neogene. It's a continued cooling trend, and it's becoming more and more arid, so cooler and drier. If we look at this diagram here, we are in this section, so we're continuing our drop towards the present day. Present day temperatures right here. Okay, so still warmer than today. Eventually it's going to get colder before it gets warmer. So there is a cooling trend, but it's punctuated with some warming events, one of which is called the Middle Miocene Climactic Optimum. Okay, so let's look at the climate on this diagram. Through the Cenozoic, which starts here and progresses to the left to where we are today. So the Neogene, so you can see the epochs, Paleocene, Eocene, Oligocene. The Neogene is this section right here. So here was the end of the Cretaceous, the warming to the Paleocene, Eocene thermal maximum, and then the downhill slope until the end of the Eocene and Oligocene, and then the swift drop there, which represents the formation and beginning of the Antarctic ice sheets. And that more or less stabilizes for a while. And then there's a warming event, and then another one, and this one is called the Mid-Miocene Climate Optimum. So it's one of these warming peaks. And then since then, things have been cooling ever since for the rest of the Miocene into the Pliocene, and then an increase in the cooling until eventually where we are today. So this shows our present day modern temperature. So most of the Cenozoic, in fact, all of it has been warmer than today. So only the last few million years has it been colder than today. Just a little perspective there. Extreme cooling at the end of the Neogene in the Pliocene epoch, that's where we see the cooling effect. So much of the Neogene, it's cool and dry but stable, but then right at the end there's a change and it becomes increasingly cold. Neogene life. There's some critters here you're going to like. Let's start with fish. Yeah, Megalodon. Quite possibly the largest shark that ever lived. There are varying estimates of Megalodon's size, with a human here for scale. Here's the largest recorded great white. kind of on the lower end of the estimates, something like this. So maybe 14 or 15 meters in length. On the upper side, maybe as much as 19 or 20. And then, of course, Hollywood would give you a much bigger shark than that. But no matter how you look at it, a significantly larger shark than a great white, more than ample to swallow you whole. So here's the typical picture of dude sitting in the jaws there. Just crazy. Multiple rows of teeth. What would they eat? It's thought that these were basically whale hunters. Why go after the small stuff when you can take down a whale? It did fine for millions of years, from the early Miocene into the Pliocene. But in the Pliocene, that's when the climate really got cold, and the whales would swim farther north into colder waters, and the sharks really couldn't follow. And so Megalodon ended up going extinct. So the genus Carcharocles Megalodon. Megalodon is the species. Carcharocles is the genus. Birds of the Neogene weren't as diverse as they are now. We didn't have that many songbirds like we do today. However, we did have Forest raucous, terror birds, large flightless birds that acquired massive sizes, and these are the descendants of the dromaeosaur dinosaurs. Although these are birds, class Aves, and dinosaurs are class Reptilia, these are the descendants of dinosaurs. Remember, birds are avian archosaurs, and these terror birds are non-avian or non-flyers. So they would have hunted much like the dromaeosaurs. They could have been solitary, but they could have hunted in packs as well. Much like some dinosaurs, which had very limited use of their forelimbs, much of the killing power would have been with the beak. So there are various forms of these terror birds. Got their start in South America, but once North and South America merged, these were one of the few successful South American lineages to have success in North America. And we found fossils of these in Texas and Florida. Don't know about Kansas. It really gets interesting now with primates. The rise of family Hominidae, otherwise known as the great apes. So primates are an order, and then the next level down is family. So the Hominidae are a family of primates, which include humans, gorillas, and others. So let's look a little more closely here. These classifications are commonly getting changed, revised, sometimes more, sometimes less. But when we look at the family level, Hominidae include all of these different kinds. Orangutans, gorillas, chimpanzees, and humans are all part of family Hominidae. Gibbons are not, they are part of another family. This family then can be separated into smaller groups, and then there's the subfamily level, which orangutans go off on their own, then the tribe level, and then the genus level. So genus Homo, of which we're a part, is there. Pan is chimpanzees. Gorillas, that's their own genus. So we're all part of the Hominidae family, just different genera. So Homo, Pan, and Gorilla are different genera. So the whole thing about humans evolving from apes isn't quite true. What is more accurate to say is we evolved from a common, more primitive primate, which is somewhere back up this way along the line. So several million years farther back. So humans didn't evolve from gorillas and vice versa. That's where humans fall in our genus Homo. So that's the human area right there. Anything that's Homo, I'd say, is basically human. So the whole Planet of the Apes thing, the OG, the original version there, Chuck Heston, it's a madhouse. I included this diagram here just to show the lineage of family Hominidae, getting its start in the Miocene. Here's the Miocene, and then branching off into two subfamilies. The Homininae is what we are a part, And then we split from the gorillas and the chimpanzees, and here's our genus, genus Homo, which really starts to proliferate in the last couple million years. What connects us with some more primitive primate is this branch right here, and these are called the Australopithecines. So these aren't in our genus, but they're probably related to us, and they're our closest ancestors. And then before them, there might have been something else that could have been somewhere in this range, and then that might have been a common ancestor for us and chimpanzees. And go even farther back, you can find others. So the farther back you go, the fossil evidence becomes more and more murky. It's harder to be definitive about some of these fossils the farther back you go. Let's take a look at some of our primitive ancestors, starting with the oldest one, and this is Ardipithecus ramidus. So this is a primitive genus of family Hominidae, commonly known as Ardi. And this is the oldest known hominid fossil, about 4.5 million years. Ardipithecus ramidus, the genus and the species. There might be a slightly older one, but Ardi here was probably about 4 feet tall, and although the skeleton I think was somewhat crushed, it was fairly complete. Here's the bone structure in the hand, a fairly well preserved fossil. We think that Ardi could actually walk upright. Some of the earlier forms, and like many of the primates today, don't do that. Or at least they don't do that for extended periods of time. So the ability to walk upright is a major step towards becoming human. It's a major evolutionary step. There are many advantages for walking upright. Okay, so for one, it frees up your other two limbs, your hands, so you can carry things. You can carry food, you can carry young, you can carry weapons. It also gives you a higher vantage point off the ground, so you can see threats in your environment. So walking upright was a big deal. We think Ardi could do that. Fairly short, like I said, about 4 feet, and somewhat stocky. Ardipithecus ramidus. Next would come the Australopithecines, specifically Australopithecus afarensis. This is a intermediate form between humans and the more ape-like ancestors, much like Ardi. So these have an age range of about 3.9 down to 2.9. So they're slightly younger than the Ardipithecines. When we look at the diagram here showing the evolution, this is 8 million down to 0. Some of the primitive possible primate ancestors that are 6 and 7 million years old. The Ardipithecines here, like Ardi, span this age range interval right here. And from them, we have the Australopithecines, and they span an age range from about 4 million down to about 3 million. And there's different ones. There's Afarensis, Africanus. Okay, and then we come to the human genus, genus Homo, Homo habilis and erectus, and finally Neanderthalis and sapiens. So the progression there, Australopithecines are part of it. They still had an ape-like brain, looking at their cranium, but a more human-like pelvis. They're still short like Ardi was. We think they walked upright also. I think they climbed trees. They didn't show any signs of making tools though. So these are some classic footprints that have an age of about 3.7 million years, and this is the classic Lucy skeleton. So Lucy is a Australopithecus afarensis. That's what Lucy was. So Ardi and Lucy. And we'll look at plant life here in the end. Yes, you have trees and flowers and all sorts of things, but grass is really flourishing and expanding. And one thing that happened with grass is it developed a form that had more silica in it. So this high silica grass would evolve, much like elephant grass, and it actually has microscopic grains of silica in there. But silica is a mineral, and it actually got a fairly decent hardness. It's like a quartz grain. So that's mixed in with the grass, and so any grazing animal eating that is going to basically be eating that silica too. And so this has the effect of, one, not tasting good, but also it wears down the teeth. So this actually led to the extinction of some grazers because their teeth weren't long enough. Over time, they'd wear down their teeth and they would end up starving and dying. And so grazers with longer teeth would fare better with these high silica grasses. So short-toothed grazers would suffer and end up going extinct. This cooler, drier climate really allowed these grasslands to spread. So savannas would have been one of the major biomes on Earth during the Miocene and into the Pliocene.